All right, so anyway, Unit 4 is actually dealing with chemical bonds. As you can see in this nice little cartoon, I love this one. This one depicts everything that more of a positive way than how I look at it. I look at it very pessimistically. You got sharing electrons, and you got some that, this looks like they're just playing around, which is really true. But ionic bonds, this one looks like he's proposing his electron. It's more like stealing in my eyes because actually the other one's stealing the electron, but they're being hippies about it. All right. So real quick, we got to go over a lot of stuff. Why do bonds occur? Why does other things happen? So this goes back to actually to the past 2 units. So why do elements bond? They want to satisfy something.
The octet rule.
The octet rule. So the octet rule, which is to have a full valence shell. They will gain, lose, or share electrons to obtain a full shell. Now keep this in mind. Only period 1, which is hydrogen and helium, they don't follow the octet rule, they follow the duet rule. Now this goes all the way back to Unit 2. So, but however, everybody else wants the octet rule. They got to satisfy those 8 electrons. Okay, so this is another little bit of review. Let's go back over how we get our charges. We go over to carbon now, take a look at him. You can see where, now remember, we only care about the outermost shell. That's the valence shell, because that's where all the bonding happens. The lower shells we don't care about because they're already filled. Anyway, he has 4 valence electrons, as you can count. How many more does he need to be happy?
4.
4 more. So is he going to have, if he gains 4 electrons, what charge is he going to have?
-4.
-4. And so if he gains 4, he's going to become -4. Same thing about nitrogen. He's missing 3. How many does he want to gain? 3. And over there at oxygen, he's missing 2. How many more should he want to get? 2. Now you should notice this, and this is a trend if you haven't picked up yet. At the top of your periodic table, I think 2 units ago, y'all put the charges above their heads. Y'all remember doing that? If you haven't done that yet, I'm going to show you that again here in a second. And so give you a second chance to actually write that down. But if you look on top of their heads, you need to note what their charges are going to be. That trend's always going to happen with these families. Okay? Same thing about their number of valence electrons. This is also going to give them their charge. I'm just giving you the basics. So remember we talked about the valence electrons. 1, 2, skip a few, 3, 4, 5, 6, 7, 8. And remember those goes with what on the top of your periodic table?
B's. Never mind.
Not the B's, the other ones. These go with the A's. The A's. Look on top of your periodic table. Do you even got your periodic table?
Yeah, right
Yeah, that's the green one right there. Yeah, take out, look at the top. So 1A, 2A, 3A, all that kind of stuff. The B's are the ones that vary. They do have a set number they begin with, but they can change them. They're like chameleons or honey badgers. They can do what they want. But we showed you this picture again of how they valence electrons are in the outermost shell. That's all this one's actually showing you, but we already kind of just talked about it. But anyway, we still use this little showing, which is a lot easier. Remember we talked about the dots and how everything goes and how many potential bond sites there are. Oh, by the way, noble gases don't like to bond because why?
They're already full.
They're already full shell. So they're going to have a charge of 0. Basically, here's the mission in this unit. Every element is going to either gain, lose, or share electrons to get a total charge of 0. That's the mission. So everything you do in this unit, you'll see charges, +1, -1. They're going to want to try to balance each other out to get to that 0 charge. That is the goal. And that's what we're going to be looking at now. But instead of looking at dots and Lewis structures, we're actually going to just be naming compounds. So again, this is going back over the charges one more time. I know this is another bit of review. But lithium has 1 valence electron. Is it easier for it to lose 1 or gain 7? Lose 1. If it loses 1 electron, it's going to have what charge? Plus or negative? Plus. It's lost electron. Magnesium has 2 electrons, valence electrons. Easy for it to lose 2 or gain 6. Lose 2. If it loses 2, it's going to have a +2 charge. Same thing about aluminum. It has 3. Easier for it to lose 3 or gain 5?
Lose 3.
Lose 3, +5. And now we get to carbon.
Either or.
Either or. He has 4 so far. Easier for it to gain 4 or lose 4. Can go each way. Most of the time, though, I will tell you carbon's mostly going to gain because he's right in the middle. That's why everything likes to bond with carbon. He's kind of a neutral party member. Anyway, nitrogen, however, once we get to this, once we go over 4, you start noticing a different trend. Instead of +1, +2, +3, ±4, now it starts going back down in number. So, for example, at nitrogen, you have 5 valence electrons, easier for it to lose 5 or gain 3. Gain 3. If it's going to gain 3, it's going to have what charge? Negative 3. And then you notice it's going to go back down as we go. Oxygen's going to end up wanting to have a negative 2 charge. Fluorine, or the halogens group, is going to end up having a negative 1. But again, we said the noble gases, they're perfectly fine. Here's the thing. These guys are not perfectly fine. They're going to give up or gain or lose these electrons that we just talked about. And that includes everybody in their family, by the way, to become like these guys. They're going to want that 8 outside shell. They're going to want that 0 charge. So, again, here's the chart that I was talking about. If you have not wrote these charges above the top of your periodic table, you need to do so right this second, because you cannot do anything in this unit without knowing them charges.
That plus or minus 4 makes a lot more sense.
Yeah, but I will tell you, here's the thing, and this is where we're going to get into, remember that jagged line? Okay, the stair-step line? The reason why it's plus or minus 4 is because technically the guys that are above that line are mostly going to be negative 4, and if they're below that line, they're mostly going to try to be plus 4. That's why really it's there. So what about these guys in the middle? If they don't have a set charge, what's going to happen to them? They're going to vary. You might want to write down that they're going to be positive. They're never going to be negative. These guys in the middle and the guys down here, which we're not even going to use anything from the lanthanide and actinide series, but mainly the transition metals, we're going to use them, but they're going to have a positive charge. They're not going to be negative. So I'll go ahead and tell you if you're ever curious about it. I didn't get to show you all this yet, but I will next time we're in lab. Sodium, for example, is a soft silver metal, and I did show you the video where they took all the metals, they put them in water, and they blew up, okay? And just like this, they cut it just like butter. And that's the guy's hand. He's actually cutting it through the metal, and it's just, the texture is like butter. Well, hard butter, not room temperature butter. But anyway, it explodes when with air because of the water in the air. And chlorine gas is a poisonous gas that if you breathe it in, you basically die. But why is it that when you put these two guys together, you get something that you can put on your rice and gravy and biscuits and all on Sunday?
They cancel each other out.
They cancel each other out. So if you take a look over here, that's a good job. So this guy, sodium, has what charge?
Butter.
Butter charge. No, it doesn't. Positive 1. And what does chlorine have? Negative 1. So by themselves, they have these charges, which cause them to, they don't like it. That's why they react. That's why they explode or they're poisonous, usually because they have these charges. But when compounds have a 0 charge, they're most of the time non-deadly. So again, if you take sodium, which is very explosive, and you put it in chlorine gas, which is very poisonous, but when you put them together, they're edible. And the reason why you can do this is because they're neutral. That charge is 0. They're not going to harm you. And that's why it's, kind of okay. So anyway, by the way, don't forget, why is this Cl have to be Cl2 and not 2Cl?
So it can balance out the...
Well, that has to do with balancing, yes. But why can't I write a 2 up here? This is one of these guys that were very special.
Because it's already got the...
What about those 7 guys I told you to remember?
Duet rule.
Not duet.
Oh.
Diatomic elements. Chlorine's one of those diatomics. Hanaf-Klebri. So that's why he has to have a 2, and that's what I meant by diatomic. However, if you notice over here, once he bonds, he doesn't need to be diatomic. He's already bonded with the sodium, so he doesn't need another chlorine. We'll talk about how these balancing work. That's actually next unit, but I'm just giving you an idea of what's going to run into for the future. All right, so this is how it actually looks, just FYI. If you ever do see a coefficient in front, we call them coefficients, or y'all call them coefficients in math. But if you see a whole number in front, that's 2 atoms that are actually separated. They're not bonded together. If you see a subscript down here like this, that means they are bonded, and they're hooked up right now. These guys are not hooked up. They're just chilling out. But then finally, when they actually react, they're going to form the reaction that you see over there. This ratio is always going to work out. Again, this is something for next unit that we're going to end up going into.
So the 2 and A means they're just 2.
2, but non-bonded. Okay. So the way I like to look at it is working out. If we do 3 sets of 10, this number is like the 3 in the 3 sets of 10, and the subscript is usually like how many reps you're doing. I know it's really weird, but if you do 3 sets of 10, how many total reps are you doing? 30. So it's kind of like the same way. Anyway, so basically this is how I view the periodic table. But how I look at it is opposites attract. So the periodic table to me is one big bar magnet. Okay? The left side is positive, the right side is negative. Except for if you exclude the noble gases. So let's just throw the noble gases away. If you actually do that, it makes sense. So therefore, the guys on opposite sides are going to want to come together. And that's going to make some neat looking bonds. However, yes, you can have guys on the same side come together, like two metals come together and two nonmetals come together. Those are two different types of bonds. But the ones we're going to be talking about for the next 5 to 6 days is going to be the ionic bond. And that is actually the most popular one. There's a lot of ionic bonds out there. All right. So again, I showed y'all this last go in the last unit. I want y'all to think left side is positive, right side is negative, but exclude the noble gases because they have a zero charge. But if you think of it like that, it makes your life a lot easier. But I will go ahead and tell you now. So we know that the guys on the left are positive, the guys on the right are mostly going to be negative. But then that's a question about the metalloids. Okay? So how do you treat them? Positive or negative? Well, here's the thing. This is what you need to know about metalloids. If they are below that stair-step line, in case you missed this a second ago, I'm repeating it again. If they are below the stair-step line, they act like more metal than they are non-metal. Okay? So if they're more metal, are they going to have more of a positive or negative charge? Positive. We're going to treat them like a positive. So if they're below the line, we're going to treat them like positives. And I'll tell you, they're like 60-40. They still have properties of both, but they're kind of right on the line. But we're going to go with their majority of how they act. So for example, like germanium and antimony, and PO, all these guys are below that stair-step line. They're going to be more metal than they are non-metal. So we're going to treat them like metals. If they are above the stair-step line, we're going to treat them more like non-metals and give them a negative charge. So you'll notice that basically that kind of settles a few debates that are out there. It makes your life a little bit easier. So basically these three guys, we're going to treat like metals because they're below that line. And these guys that are on top, we're going to treat like non-metals. In other words, have a negative charge, in case you're wondering. There are some weird rules when we get to this line. Writing formulas, this is what we're going to talk about today, and actually this is where we're going to get started but not really go too much into. Either you're going to have a positive ion and a negative ion. Here's the thing. Yes, this is where we get to the sexism. Okay? The positives are on the left and the negatives are on the right. In other words, the positives take the first name and the negatives take the last name. Okay, sort of. Okay? So you know how like people get married, then they take the last name? Yeah, there you go. The girls, well, I'll get to how to change their last name. But basically, this is how it goes. The positive is listed first. So the metals are going to be named first. Non-metals are going to be named second. And yes, mostly the non-metals are girls. Here's the other thing, though. This guy keeps his name. He just says his name. Okay, like calcium, sodium. They don't change their name. However, you might notice that whenever you say sodium chloride, you say sodium chloride, not sodium chlorine. Well, there's the reason why. The last name has to change the last few letters to IDE. Okay, so anyway, you need to know the subscripts. And that tells you how many parts for each one, which obviously you already know that. So let's actually do some quick examples. So for example, everybody knows salt. The reason why it is just 1 and 1 or a 1-to-1 ratio is because, well, +1 charge, -1 charge. Where am I getting these charges from?
From the thing up here.
From the periodic table. By the way, a lot in this unit, I'm going to ask, where am I getting these charges from? The answer is going to be periodic table that you wrote down on the charges on top. This is not cal, it is calcium oxide. But if you'll notice why it's a 1-to-1 ratio, calcium has a +2 charge, and then oxygen's a -2. They balance each other out. That's why it's a 1-to-1 ratio. But what if they're not balanced? They don't have a 2-to-2 or a 1-to-1. Okay, well then you got to start doubling them up, and that's where your subscripts come into play. So for example, magnesium has a +2 charge. He's in the second group. But chlorine has a -1. Okay? But we have to give it 2 times the amount of chlorines because each chlorine gives in a charge. So if I have 1 chlorine, it's -1. If I have 2 chlorines, it's -2. Does that make sense? So basically, every time you add a subscript in, you're doubling, tripling, whatever.
What would you do if you don't have the ×2? Would you be able to?
Well, when they would come together, the overall charge would be -1. You got to remember, they will not be -1. They have to be 0. So your goal is to get these guys to 0. That is the whole mission of this whole unit. So just like down here, that's where we end up getting these weird little ratios where you got to actually multiply to figure it out. But a lot of it's knowing the common denominator. And most of the time it's 2 and 3, and then you're pretty much, you already know what the common denominator between 2 and 3 are. What do 2 and 3 have in common? 6. So you want to make the +2 charge 3 times to make it 6. And then you want the -3 with the times 2 to make it 6. And so 6 plus 6 minus 6 gives you 0. And so that's the main idea. Now, I will tell you, there is a trick to doing this, okay? Whee! So, some people, and this is kind of like the question you just asked. So let's say you want to bond lithium and sulfur together, okay? You cannot just squish, all right? Let me squish this bug real quick. There's no squishing in this class. No squishy. This will not work. Why? Look at their charges. What's the charge of lithium? +1. What's the charge of sulfur? -2. If you do +1 with -2, you're going to get an overall charge of -1. You cannot have that. They want to be like noble gases. They want to be 0. You have to get it to 0. So you can't. The only thing you can do is double up. So this would be incorrect, but this is correct down here at the bottom, where you actually have to double it. You could say at one time when I made this slide that I was like I had a lot of trouble with people not figuring that out. The overall charge must equal 0, so how do you make it the neutral charge? Well, you then have to double it up, and that's really all you had to do.
So that's why that 2's down there.
And that's why that 2's down there. So do realize this 2 goes with the lithium. It does not go with the sulfur. Remember, everything's kind of backwards in chemistry. Normally in math class, you put a 2 in front, it distributes, and that's going to happen a little bit later. But down here, know that 2 goes with 2 lithiums and not 2 sulfurs. That's why we use subscripts versus whole numbers in the front.
So you take whatever you use and to make that number where it'll make that 0 and use it as a subscript, put that down there?
Right. That's why that's a 2 down here.
Okay.
And so there's actually an easier way of doing this. So a way that this will always work, and this only works with ionic compounds. It does not work with covalent. So all we're doing for the next 6 days is ionic. All you do is you list those charges. So let's take our same example we just talked about, which was lithium sulfur. +1, -2. Guess what? Here's a step-by-step process. Number 1, drop the signs after you write them. Okay? So you get to this part right here where you put their charges above their heads. Yes, put their charge above their heads. Can I put them off to the side? No, put them above their heads. So after you do that, take off the +1, take off the -2, okay? And then you got 1 and 2, right? You just crisscross them. And then you're done.
That's all.
That's it. So list their charge above the head, drop the sign, crisscross, and you're done. Well, now they're like fractions. You got to draw, if they are, like for example on the second guy here, that is an exception. I did forget about. For example, if you look over here, when you do this with calcium and sulfur, +2, -2, drop the signs, you end up with 2, 2. You can't have that because 2 over 2 is really what in fraction form?
1.
1, or 1 over 1. So if you can reduce, and most of the time it's going to be even numbers, but if you get 3, 6, you got to reduce that to 1, 2.
So if it has the same subscript, you can reduce it to make it just...
Yeah, you have to reduce it. That is not an option, because that's the only one thing, but this is the quickest way to get there. And so that's basically the main idea for today, is actually knowing to crisscross charges and be able to list them right. It would be 3 and 6, it would be 2. But we do not list the number 1 down here. So like when we do crisscross, in chemistry we don't like writing 1. Well, it's self-understood there's a 1 down here. Okay, but any other number you have to write. Does that make sense?
Correct.
Drop the sign, cross them. If you're not reduced, you need to reduce them. Just like this guy over here, it was 2 and 2, so we have to reduce it to CAS. If you do not reduce it, it will be counted wrong. Boom, 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 boom. Okay. So in case you missed some of that, remember the positive's always on the left and negative's on the right. If for some reason you have one with the negatives on the left, that's me messing with you. You need to put the positive on the left and the negative on the right. All right. So let's try some bonding subelements here. if you haven't got a sheet of paper out or somewhere on the side of your notes, go ahead and try bonding these guys together. Take sodium, bond it with chlorine. Take sodium, bond it with oxygen. Be sure you get their charges and crisscross. That's what we're doing here. We'll go over here in a second. So what we're going to do, I'm going to show you these real fast. Now, again, don't be embarrassed because a lot of people don't know what they're doing. If you don't, that's okay. But when you see one up there and you're like, why is it this? Ask me. Okay? I'm not going to make fun of you. Okay? I promise. That you have my, I swear. I do make fun of people, but not all the time. Only on TV. All right. So looking at the first couple ones. Some of them are like kind of common that you kind of heard of. But first one should be NaCl. Second one should be Na2O. The next one should be LiCl. Next one is CaCl2, CaO. And then you get down here near the bottom, we start seeing some interesting stuff. Li3N. Any question on that one? Okay, what about the very last one? Do I need to show you that one?
Are you going to make us work these backwards?
Yes. Oh. Backwards is way easier because all you do is just say their name. Yeah. Like there's no number needed, so you don't even have to worry about it. Oh. So like on the very last one, calcium has a +2 charge, and nitrogen has a -3. So when you see these guys, you drop the sign, and you just crisscross. And so Ca3N2. So calcium has a +2 charge, oxygen has -2. So when you crisscross these guys, you drop the sign, and so you end up having this. However, it's just like saying 2/2. If you can reduce it, you got to reduce it. That's why it would be Cal. Remember, the crisscross method only works with the ionic compounds.